Okay, class. So there was some want from people in office hours to have solutions for the lecture problems. So it was easiest for me to just make a video. There's also, we're not going to be able to get your homework, oops, I think that's homework 5 solutions graded to you before the midterm. So I was going to just put them on this video. That will mean that you won't be able to redo the problems for this assignment, but I think it's better to kind of know what's going on for the midterm. Okay, so let me start with the lecture problems. This is lecture 11. You can find these all in the discussion sessions or in the files folder. So the first one was prove from the axioms that minus c is equal to c for all c and r. Okay? So what this means, well, so what do we have to, what we'll do is look at, what do we have to prove? If you want to prove that something is minus blah, in this case minus c, you need to show that this, so this something plus minus c is equal to 0. Okay? And then that by definition means that it's additive inverse. But of course we already know that c plus minus c is 0 because minus c is the additive inverse of c. So therefore this something is is c. Okay? So that's just straight from the definition, and probably at some point I should say this is the difference between this and this, but since addition is commutative, we can say this. Okay? All right, so that's part A. Part B was we wanted to prove that AB is equal to negative A times negative B. Okay, so what we do here is we do a trick where we kind of add 0 in. So let me write it this way. So I have negative A times B plus minus B. So I should say 0 is A times 0, which is, negative A times 0, which is negative A times B plus minus B. By distribution, this is negative A times B plus negative A times negative B. So the reason I've done this is, well, it's introduced one of the terms that I'm interested in. And what I know now is that negative A times negative B is the additive inverse of negative A times B. Okay? Of course, I can also write this is equal to 0 times B, which is A plus minus A times B. Again, by distribution, this is AB plus negative A times B. So now these terms are the same. It's both negative A times B. This term is one side that we're interested in. This term is the other side interested in. So both AB and negative A times negative B are additive inverses of negative A times B. And therefore, since we know additive inverses are unique, you get that they're equal. Okay? All right, so let me go to lecture 12. Let me pull it up. Okay, so here we had to show that from the axioms, we wanted to know what is the sup / inf of the set A, which was 1 over n in n. Okay? So first, well, the supremum is 1, and infimum is 0. Okay, so how do we know this? Well, the claim is that, I mean, if you want to show that something is a supremum, you first have to show it's an upper bound. So the claim is that 1 over n is less than 1. I'm being a little more careful here than I expect you to be on the midterm. Okay. So in particular, then we know that 1 minus 1 over n, we're trying to show that 1 minus 1 over n is greater than 0. We can multiply by n. On both sides because we know positivity is preserved by multiplication. So really we can start with n minus 1 is greater than 0. This implies 1 minus 1 over n is greater than 0, and this implies that 1 is greater than 1 over n for any n. Okay, so 1 is an upper bound, and it can't be, it's the least upper bound because 1 is in the set. So in particular, 1 minus epsilon is not an upper bound for any epsilon greater than 0 because, well, 1 is greater than 1 minus epsilon. Okay? So there, and 1 is in the set. Okay? So that's the supremum argument. For the infimum, this uses Archimedean property. Again, it's clear that 0 is a lower bound because all of these things are positive. Okay? And for the infimum, well, for any epsilon greater than 0, there's some n greater than 1 over epsilon for n in n. Okay? This implies that 1 over n is less than epsilon, so epsilon is not an upper bound. Okay, for 2, we just had to construct two functions. So we have f, g from some domain to the real numbers so that f of x is less than or equal to g of x, but the infimum of g of d is less than the supremum of f of d. Okay? I won't write out a specific example, but it will look something like this. Well, g could be, maybe I'll just make this a closed interval. This will be my graph of g. And this, so f just has to be bounded below by it. Okay? And this is f. So g and f. Notice this will be the supremum. This will be the infimum. And here is the supremum of s. So we have supremum of f, infimum of g. Okay, so I'll let you write out a specific example, but that's the basic picture. The problem, I mean, so it just occurred, the supremum of f occurs at a different place than the infimum of g. All right, let me go on to lecture 13. Let me pull it up. Okay, so we have to prove the Archimedean property. And also prove that square root of 2 is not rational. Okay, two good things to do. Okay, so how do we do this? Well, maybe I'll do the second one first. Okay, just because it's a little shorter. It's a proof by contradiction. And maybe I'll even say a little more about it. So we have square root of 2 is equal to a over b. So suppose square root of 2 is a over b, where a and b are integers, and they're relatively prime. So the GCD of a and b is 1, okay? This is an assumption that we can always make, right? By properties of the rational numbers, there's always a representative where the GCD is 1. Just divide it out by all the common factors. All right, so then what happens? Well, we square and we bring the b over, so we get 2b squared is equal to a squared. Now what has to happen? So since a squared is even, right, since it's equal to 2b squared, we would have a is even. Okay? Which implies that 2b squared is divisible by 4, right? Because a squared, so this what we would have is 2b squared is 2c all squared, which is 4c squared. But then now b squared is 2c squared. So this implies b squared is even, which implies b is even, which implies the GCD of a and b is greater than or equal to 2. Okay, so that's the contradiction. So maybe I'll just make one note, like how do you show that other numbers are irrational? Okay, so if you want to say a square root of 3 is not rational, you would do a very similar argument, right? So you would say, well, a squared is equal to 3b squared. This is now, so a squared is divisible by 3, then a is divisible by 3, divisible, which implies, well, again, a squared is divisible by 9, so b squared is divisible by 3, and finally, that should tell you that b is divisible by 3. And then you're done, okay? By the same argument, you can assume that the GCD of a and b is 1. So what gets a little bit trickier, I won't write this one out, but on the homework, people often gave square root of 6 as an example. You have to do something else, to work out why that should be, right? If I have something like square root of 8, it will also be irrational. Again, it's a little more work because now you don't have just one prime number here. You have 2 primes or a power of primes. So in any case, it turns out the key thing to say is uniqueness of prime decomposition. So once you know that there's kind of a unique way to write the primes of a and the primes of b, it's reasonably easy to show that square root of n is not q unless n has squares in prime decomposition. Okay, by which I mean that if I look at the exponents, they're all divisible by 2. So it looks like some prime times to 2 to the n's. So another prime times 2 to the m, or raised to the 2 to the nth power, etc. Okay, let me go on. So the Archimedean property. Okay, so what we needed to show is that for any real number z, there exists some n greater than z. Okay, so n is in the natural numbers. Okay, so what you do is you say suppose not. Okay, so suppose not. So this implies that the natural numbers are bounded, right? since they're all positive, there'd be some bound and in particular then there would be a sup. Okay, so therefore the sup of the natural numbers would be in R. Okay? And now what happens? Well, you would say, take your, here's sup. So I don't know, let me call it S. I'll call this S. Here's the sup of the naturals in the real line. What I know is that for any epsilon, there has to be a natural number here. So S minus, for any, let's just say epsilon is a half, I know that there would have to be some natural number in between S minus a half and S. Right? And the reason is otherwise S minus, S wouldn't be the supremum. S minus a half would be a lower upper bound. Okay? But then just adding 1. So then S plus a half is less than n plus 1 is less than S plus 1. And in particular, S is now less than n plus 1. Okay, so that's the contradiction. If you find an n here, you're going to find an n plus 1, which is larger, so it can't be a supremum. I mean, so what's kind of, bad about this argument, I should say, is that it doesn't work for the rationals. So, exercise, prove for the rationals. Right? What I mean, only using the rational numbers, not just, not assuming anything about the existence of the real numbers. All right, so that was lecture 13. Let me do lecture 14. Apologies for doing this in real time. It's kind of slowing me down in some places. Okay, so we have F0 be 0. We get to, we're making a sequence now. F1 is 1. Fn plus 2 is equal to Fn plus Fn plus 1 for all n greater than or equal to 2. Okay, so we have the famous Fibonacci sequence. All right, so what we need to show is that the sum from I equals 0 to n of the f sub i's is equal to f sub I plus 2. Okay? So how can we do this? Well, it's going to be proof by induction. I mean, you kind of are forced into doing it. Okay? So proof, induction starting, well, you have to starting at n equals 1 doesn't really, well, okay, in this case, I guess I want to start at k equals 0 by the way that I've set it up. So k equals 0 is just saying f0 plus f1 is equal to f2. Okay, that's by definition. Okay? So we're assuming it's true for k. Okay, so we have the f sub i's is f of k plus 2. And now we take the sum, so f0 plus f1 plus fk plus fk plus 1. And you want to show that this is equal to fk plus 3. Okay? So this, by induction, is equal to fk plus 2 plus fk plus 1. By definition, this is equal to fk plus 3. Okay, and that's it. All right, so for the second problem, you want to prove the triangle inequality. So question 2 prove that the sum of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Or the absolute value of a plus b is less than the sum of the absolute values. So you can do this essentially by just checking, whether a is positive, a is negative, b is positive, b is negative. So you get like four different possibilities. I'm essentially going to do this, just kind of combine some cases. So what you have is that a is bounded above by, or below by negative absolute value, and above by the absolute value. Same for b. And now you can just add, okay? So what you get is that negative a plus negative b, which is just negative a plus b, is less than or equal to a plus b, and that's less than or equal to a plus absolute value of a plus absolute value of b. Okay? So you always get this gap for where a and b can be, and of course, if a and b are both positive, you're here. If a and b are both negative, you're here. And then if they're different, if a is positive, b is negative, you'll get something in the middle. Okay? So let me go to lecture 15 now. Okay, so you want to come up with a bounded sequence that does not converge. So in this case, you can just say 0, 1, 0, 1, 0, 1. Now, I claim that this doesn't converge, but we'd like to prove it. Okay, so I think it's useful to say, so how do we prove doesn't converge to x? Okay, so here's a kind of useful criterion. Okay, in this case, I think you can prove it directly. Okay, but what you can show is that if a sequence converges to x, then for any epsilon greater than 0, there exists some n in n, so that xn minus xn plus 1 is less than epsilon for all n greater than or equal to n. Okay? So what this is saying is that consecutive terms of the sequence should start getting very, very close together. Okay? And the reason for this is just the triangle inequality. So maybe I won't write it out completely, but what we know is that xn minus xn plus 1 is equal to xn minus x, less than or equal to, plus x minus xn plus 1. Okay, so I just put in a plus or minus x here. And now for large enough n, this is less than epsilon over 2, and this is less than epsilon over 2 for some, n greater than or equal to n. Okay? So since they both converge to x, you'll be able to show that both of these have to be less than epsilon over 2, and therefore the difference between the terms has to be less than epsilon. Okay, so the picture looks something like this. Since they're both close to x, they can't be that far apart. Okay? And therefore, since, the distance between, so since 0 minus 1 is equal to 1, we have that this can't possibly converge to a real number. Okay? Again, this is something where you could just kind of check where just plug in a real number, work out that it can't converge, but this should be useful in general. Question 2 is you wanted to prove b over n converge to 0 for any b in the real numbers. Okay? For n and n. Okay, so what you want to show is, let me just write it out. So we have to let epsilon greater than 0. What we need, so we need to show the absolute value of b over n is less than epsilon for all n greater than or equal to some n, okay, which we have to find. And of course, it's nice to do absolute values since I don't care whether b is positive or negative, okay, or 0, right? It could be 0. Okay, so what happens? Well, since 1 over n converges to 0, we know that there exists some epsilon, some n in n, so that 1 over n is less than epsilon over, and here I do have to be a little careful, absolute value of b, okay, for all n greater than or equal to n. Okay, since the absolute value of b is a positive number. Okay, so actually what I should say is, if b is 0, I'm done, right? The sequence is just 0, 0, 0, 0, 0. Okay, but if I have something like, negative a half, I have to prove something. All right, so therefore, for this n, for such n, we have the absolute value of b over n is equal to the absolute value of b over the absolute value of n, which is just n. So this is now less than epsilon, okay? And that's it. Okay, so the n that you choose for epsilon over b is the same n that you choose for less than epsilon for the new sequence. Okay, so now let me go to the homework. Okay, so I won't give as many details as we would expect of you, okay, just because the video will be long. Okay, so this is just to give you the idea of how to do all these. Okay, so the first one, and I'm going to do the group homework, not the individual, just because there's more problems. Okay, so we want to show the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b. Okay? So unfortunately, I think maybe there is a very clever way to do this. But of course, what you can also do is just list the cases, okay, which I'm going to do. So we have, a and b are positive. One positive, one negative, and both negative. Okay? And notice also we can assume that a is strictly greater than b because both quantities are the same if a and b are switched. Okay? So if I take, this quantity minus, and I flip a and b, then I'm getting the absolute value of b minus the absolute value of a, but then I'm taking the absolute value. So I get the same quantity. Same thing here. Okay? So then, so a I'm assuming is greater than b. So if a and b are both positive, then these are just saying a minus b is equal to a minus b. If a and b are both negative, then I have the absolute value of a minus the absolute value of b is equal to the absolute value of negative a, right, since we've assumed that a and b are negative, minus b, which is equal to the absolute value of negative a plus b, which is equal to the absolute value of a minus b. Okay, by what I said, the absolute value of b minus a is the same as a minus b. And if a is positive, b is negative, remember this, we don't have to assume the other case, because I'm assuming a is greater than b, then what we're looking at is the absolute value, in this case we have a minus the absolute value of b, since a is equal to the absolute value of a. And the claim is this is less than or equal to the absolute value of a minus b. Now, in this case, we know that a minus b is equal to a plus the absolute value of b, okay, since b is negative. And therefore, this is equal, since now we have two positive numbers, this is a plus b, absolute value of a plus the absolute value of b. On the other hand, this one is less than or equal to the absolute value of a plus the absolute value of b by the triangle inequality. Okay, so since these are the same, this is equal and this is strictly less than, we're done here. Okay, so let me do part 2. So we need to come up with counterexamples to the nested interval theorem. So let me just, again, I won't provide all the details. So A, we have the intervals are allowed to be open. Okay, so I'll just look at the interval 0 to 1 over n equals in. And the intersection of these is going to be empty. Okay, so the way that you show that is you'd say, well, if you take any element in the intersection, it has to be, in particular, it's less than 1 over n, and strictly greater than 0. Okay, so it can't be any negative, it can't be 0, and any positive, you're going to find some 1 over n where this is false. Okay, where it's not contained in them. All right, for part B, in this case, you can just take, negative 1, negative a half, 1, 2, okay? And just set this to be I1 and this to be IN for all n greater than or equal to 2, okay? So the intervals aren't nested because, this one doesn't have any intersection. But since to show, if you want to show the intersection is empty, well, it turns out I1 intersect I2 is empty, and therefore the intersection of all of them has to be empty. Lots of examples for that one. All right, so for Kn intersection n in n, Kn is empty, I'll just say this is the proof, proof follows from Archimedean property. Yeah, sorry, I'm realizing I don't want to, give full details just because the video will end up being an hour long. So the proof is, well, we showed by the Archimedean property that for any real number, there's some natural number greater than it. Okay, in particular, if I fix a natural number, all I have to find to show the intersection is empty is some number of these intervals where that real number is not in there. Okay, and just, that's exactly what Archimedean gives you. Okay, so let me give maybe a few more details for this one, okay, because there's a little more involved. Okay, so In is An Bn. We're assuming the infimum of this is 0, okay? And then you want to show that there's a unique x in the intersection, okay? So of course we know that there is, so by, nested interval property, we get 1, right? We get x in the intersection. Okay, for all n. Okay, and you want to show that there can't be 2. So suppose there's 2. Okay, so x and x prime are in IN for all n. Okay? And I can assume that, say, x is less than x prime. Okay? I mean, it's got to be, it's one or the other, right? So what we have, so therefore we have that the a sub n's are less than or equal to x, which is less than x prime, less than or equal to b sub n for all n. In particular, I get bn minus an is equal to bn minus x prime plus x prime minus x plus x minus an for all n. And these, so this is positive or greater than or equal to 0. This is greater than or equal to 0. So therefore, I have that this is greater than or equal to x prime minus x. Okay? But this is greater than 0. Okay, so since this is true for all n, it implies the infimum of the an and bn are not equal to 0. Okay, so that's that problem. All right, so for 5, you had to show n cubed minus 6 is greater than or equal to n squared for large n, and actually in this case this is just n greater than or equal to 3. Okay, so for n equals 3, you can just check. This is 27 minus 6 is greater than or equal to 9. Now you want to prove this by induction. Okay, so let me just say we're assuming it's true for p of k. Okay, and then what we want to show is p of k plus 1. So in particular, we have k plus 1 cubed minus 6. Well, this is k cubed plus 3k squared plus 3k plus 1 minus 6. This is greater than or equal to 3k squared plus 3k plus 1 plus k squared by induction. Okay, so this is equal to 4k squared plus 3k plus 1. And this is greater than or equal to 0 since k is greater than or equal to 0. Okay, so it's something that you don't really need the full assumption on k, except that it's false for the base cases 1 or 2. But once you kind of have a place to start, everything else just follows immediately. Okay, so let's apply this. Okay, so we have the sequence 4n cubed plus 3n over n cubed minus 6. Okay, and we want to show that this converges. Again, this is something where you just have to guess, essentially. And here it turns out that, the guess is that the limit should be 4. Okay, and that's essentially because these terms are the same. Again, this is just something where this just shows that it's difficult to show convergence in general. You have to get, you kind of have to know the answer before you can prove it. Okay, so what we have is 4n cubed minus 3n over n cubed minus 6 minus 4. So we want to show this is less than this epsilon that we're given. Okay? So well, this is 4n cubed minus 3n over n cubed minus 6 minus 4 times n cubed. Okay, so this is equal to 4, oops, sorry, the 4n cubed goes away. So we just end up with 24 minus 3n over n cubed minus 6. And now by our assumption, this is less than or equal to 24 minus 3n over n squared, which is less than or equal to 24 over n squared, leave off the absolute value, plus 3n over n squared. Okay, so I'm skipping some steps here, but this is triangle inequality and then applying the fact that absolute value of minus 3n is 3n. Okay, and now what we know is that this goes to 0. Okay, so in particular, I can find n so that 1 over n squared is less than epsilon over 48, okay, which will make this less than epsilon over 2. Here, this is 3 over n, so I can find an m so that 1 over n is less than epsilon over 6. This will again give me a less than epsilon over 2. And so adding them together, I get less than epsilon, okay, for like the max of n and m. Okay, so let me do 7 now. So we need to prove that 12n to the 5th plus 3n to the 4th over 2n to the 5th minus 1 converges. And again, we kind of just have to guess that it converges to 6 in this case. And again, that's because the leading exponents are the same. So I have 2n to the 5th minus 1 minus 6. Well, this is again equal to 12n to the 5th plus 3n to the 4th minus 12n to the 5th plus 6 over 0. I mean, one way to check, oh, sorry, not over 0, over 2 to the n to the 5th minus 1. One way to check that, you know, you're on the right track with convergence is that these higher n terms are supposed to cancel, right? If you don't have that, you'll never get something which goes to 0. So we end up with 3n to the 4th plus 6 over 2n to the 5th minus 1. Similarly, in this case, we're going to have that 2n to the 5th minus 1 is less than n to the 5th. Maybe I can get less than or equal to n to the 5th. Oh, sorry. Greater than or equal to n to the 5th. Okay. So we can make the replacement. I just have to be careful at 1, but I think I'm okay. So this is less than 3 to the n to the 4th plus 6 over 2n to the 5th. So I get less than or equal to 3 over 2n plus 3 over n to the 5th. Okay, I won't go through all the details. Again, this goes to 0. This goes to 0, so you can find terms where they go to less than epsilon over 2. Okay? All right, so for 8, we had a sequence of positive real numbers. And you wanted to show it converge to S, so Sn converges to S. And you want to show, well, maybe I'll give the, well, okay, I'll do the argument. So if S is 0, we want to show square root of Sn converges to 0. If S is equal to 0, we want to show square root of Sn converges to square root of S. Okay? So for the first part, it's slightly simpler. So what we have is we want to show let epsilon greater than 0, and we want to find some n so that square root of Sn is less than epsilon, okay, for all n bigger than or equal to n. Now we know there exists some m in n so that Sn is less than epsilon squared. Okay, for all n and n. And therefore the square root of Sn will be less than epsilon. Okay, that's it. And where n is bigger than m. Okay, and then that's the n that you choose. So you say Sn is less than epsilon squared. That n is going to be the one that you use to show that the square root of Sn is less than epsilon. Now, for the other case, where Sn converges to S, what you want to show is the square root of Sn minus square root of S is less than epsilon, okay? And you know that you can bound Sn minus S. Okay, so in this case, note that S minus Sn is equal to the square root of S plus square root of Sn times the square root of S minus the square root of Sn. And you can think this part we know about, right? This we can make small. This is what we're interested in. And this should be bounded. Okay? So, in particular, since this is some bounded number, and this is within, epsilon of it for, epsilon, or for n large, in particular, this is less than or equal to twice the square root of S plus 1. Okay, because, this is eventually going to be less than S plus 1, and so is this. Okay? So what you want is n in n, so that S minus Sn is less than, I believe, epsilon times square root of S plus 1. Or twice that. Let me see if that's right. So then we know that S minus Sn is equal to square root of S plus square root of Sn times square root of S minus square root of Sn. You know that this is is strictly less than epsilon times 2 square roots of S plus 1. This is less than or equal to 2 square roots of S plus 1. So if we divide both sides, we get square root of S minus square root of Sn is less than epsilon. Okay, so finally, we have the absolute value problem. So let me just bring it up here. So you want to show xn converges to 0 if and only if xn converges to 0. And then you want an example where, in general, convergence of absolute value doesn't imply convergence of the xn. Well, the first one is pretty simple, or the second one is just pretty simple. If you look at 1 minus 1, 1 minus 1, and so on, then absolute value converges, but x doesn't. Okay. For the second part, what you show is that you're looking at terms like this, absolute value of the absolute value of xn. You want to show this is less than epsilon. Sorry, so I guess I should say I'm showing this direction. Okay. We know that the absolute value of xn is less than epsilon for some n bigger than or equal to n by convergence of the xn's. And therefore, this is equal to absolute value of xn, so we get convergence of the absolute value. Okay? On the other hand, if you know that the absolute value converges to 0, and you're looking at the terms xn, again, you want to find some n so that this is less than epsilon. But again, this being 0 means exactly, well, that it converges. So there exists some n in n, so that absolute value of xn is less than epsilon for all n bigger than or equal to n. This implies the absolute value of xn is less than epsilon. Okay? And that's it. All right, so thanks. See ya.